Hey everyone, welcome back to the It's a Material World podcast. I'm Puneeth. I have my co-host David here. How's it going, David?
It's great. I'm super excited to be here today. And the episode we're going to share today is really exciting. We sit down with the SVP of Materials Research of Carbon 3D. And what are you looking forward to?
I was just fascinated really with like all of the sporting goods applications of their technology. So they make the midsoles for Adidas running shoes. They also make inserts for Rawlings baseball gloves. So I played baseball for like 15 years up until the end of high school. And so that was just cool, kind of just to see the sporting goods industry applications of 3D printing. But yeah, it was just really fascinating to hear about the technology. He's the senior vice president of materials, so he actually gets pretty technical, which is kind of an interesting twist on our episodes. Usually we stay high level, but this was really interesting how he dives into the dual chemistries and the processes and just even the development of new materials. So yeah, that was something that I would definitely recommend tuning into. What about you?
Yeah, I think that just it's a unique experience to be able to talk to an SVP just because they have the technical know-how to obviously get to that level, but they really have the entire vision because they are the ones driving it. And so they are in a unique position to kind of shape how we use this novel technology. So it's really interesting picking his brain and hearing what he thought about the technology, the limitations, the benefits, and then finally the applications. And so he was just like such a unique place where he knows everything, he controls so much that he gives great insight and really is just experience that gives a lot of deep learning to the application that we're talking about. So I thought it was
Yeah.
a super interesting conversation the entire time.
Yeah. And speaking of deep learning, I mean, machine learning, AI, I think that also kind of came back to this conversation like it has with previous episodes. But this one is really cool because they talk about the design engine software that Carbon released and how that's kind of like publicized now and available for even like students and individuals to use in addition to how they implemented to create their own products. So that was cool. It was a different twist. Usually we emphasize, the importance of computational material science, ML, AI, and its potential in this industry, but to see it kind of make its real world impact and be used today was also really cool. So yeah, a lot to look forward to in this episode. Make sure to leave a rating and review for us. It would really help us out. And yeah, let's get into the episode.
Our sponsor today is Johnson Matthey. Are you a material scientist or engineer who wants to be part of the drive for a world that is healthy and cleaner, both for today and for future generations? By understanding the relationship between a material structure and its physical properties and chemical behavior, material scientists and engineers at Johnson Matthey develop sustainable technologies that are catalyzing the zero transition in transport, chemicals, and energy. They design porous materials for catalyst supports for emission control systems that remove harmful emissions produced by diesel and gasoline engines. They innovate new compositions for catalysts at the heart of the hydrogen fuel cells in trucks and buses. And they also develop new corrosion-resistant reactors for processes that enable the production of sustainable chemicals and fuels. To find out more, visit matthey.com, that's MATTHEY.com. Johnson Matthey, inspiring science, enhancing life. Hey everyone, we are super excited today to welcome today's guest, Dr. Jason Rolland, Senior Vice President of Materials at Carbon. As SVP of Materials, Jason is tasked with creating the broadest possible range of materials for growing 3D objects with Carbon's DLS technology. Previously, he was also the Senior Director of Research at Diagnostics for All and also co-founded Liquida Technologies. Jason holds a BS in chemistry from Virginia Tech and a PhD in chemistry from UNC Chapel Hill, on top of holding 25 current and pending patents. Thank you so much for joining us today, Jason. We're super excited to talk to you.
Really happy to be here. Thank you.
Seems like we have some like location commonalities here. Like David's from Virginia and then I'm from North Carolina. So you've
Oh,
kind of
nice.
like yeah, there's that similarity there. I have a lot of friends at UNC.
Awesome.
But that's kind of besides the point. We'll get into Carbon's technology. So you use 3D printing to produce end-use products at scale, such as 3D printed midsoles for Adidas or 3D printed inserts for Rolland's baseball gloves. So they're very cool products, but they start off as like a liquid polymer called polyurethane. And so I was just wondering if you could kind of talk us through this material, the properties, and where we may see polyurethane in our daily lives.
Yeah, sure. So polyurethanes were invented quite a while ago, I think likely in the 50s or 60s. And there's a couple of key attributes that they have. One of them is just the versatility of the polyurethane class of materials. By changing the building blocks, you can have everything from a really soft, stretchy elastomer all the way to a very rigid, tough, high impact strength type of material. And so it was, as a class of materials, it was very appealing to us when we first started building out our material portfolio because of that versatility. So you would encounter polyurethane materials in all kinds of places. So maybe the most recognizable place would be foams. And so soft, cushy foams like in your automotive seating or in your mattress or in your pillows, ranging to, there's foams in refrigerators that help insulate things. And so those are all generally made of polyurethane. And this includes some of the benchmark materials that we were up against. Boost is a really famous midsole material from Adidas, and that is made of polyurethane pellets that are then fused together during production. And so Boost would be a polyurethane foam with very, very high energy return. Other places you might encounter spandex. So spandex fibers are another really famous brand name of a polyurethane. So again, that stretchy type of fabric. And on the rigid side, some other applications that you might not be aware of. So bowling balls actually have a significant amount of polyurethane in them, as well as skateboard and rollerblade wheels. Those are made from cast polyurethane, more obviously on the rigid side in that case. So yeah, as a class of materials, they're extremely useful, extremely widely used in a range of industries.
Interesting. So I was just wondering, you mentioned the range of polyurethanes from flexibility to rigidity. What exactly about the material allows for that versatility? Is it like the cross-linking like extent that creates that rigidity, or is it like the rigid pendant groups? I don't know. I'm just trying to tie back to my polymer science class.
Yeah, no, it's great. Great question. And in fact, it goes back to the origins of polyurethane. And I'm not an expert on the history there, but rubber materials are generally, natural rubber materials are cross-linked. So this is work done by, Goodyear and others early on, where you can take natural rubber from trees or synthetic polyisoprene and cross-link that with sulfur compounds. But once you cross-link that object, even though it's an elastomer, it's now a thermoset, meaning that when you heat a car tire, it will not flow, it will not melt, it will burn before it melts. And so this is a limitation. It means it's tricky to process these materials and tricky to make forms out of them. Polyurethanes, or at least a subcategory of polyurethanes, are what is called a thermoplastic elastomer, meaning that it is an elastomer just like natural rubber, but it can flow when heated. And so the way that polyurethanes do that is you have what's called a hard segment and a soft segment. And so your hard segment will have a very high TG, and you have these sort of short runs of, really it all comes down to hydrogen bonding. So you have these short runs in your polymer chain of these hard segments, and those will crystallize together and or align together, they'll pack together. And they form what's called a physical crosslink. So you have that instead of a covalent bond crosslink. And then you have your soft segment of your polyurethane. And that is typically has a very low TG. And so at room temperature, you're above the TG of the glass transition temperature of the soft segment, and you're below the TG of the hard segment. So you have this nice stretchy rubber material. So I guess the analog in natural rubber that material wants to flow because you're also above the TG, but it's held together by chemical crosslinks with covalent bonds, whereas thermoplastic polyurethane elastomers are held together by these physical crosslinks. Now, in terms of versatility, so you can change the chemical identity of your soft segment. You can change the molecular weight of your soft segment, and that will dramatically alter the properties of that resulting polyurethane material. You can also change the hard segment chemistry. So this all comes from isocyanate chemistry. And so there's a variety of different flavors of isocyanates that one can put in the polymer, and each one results in different properties. And so you can play a lot of mixing and matching and formulation work to kind of fine tune the polyurethane material for your application.
So I think that was a great explanation of how we can modify the polyurethane that we call into multiple forms, but maybe a broader view is for carbon specifically, you're trying to 3D print it. So with that in mind, what are some of the specifications that you change to 3D print it, and what are important, and maybe also why polyurethane versus other materials that could be 3D printed?
Yeah, excellent question. So this gets to kind of the core of our big technological breakthrough around materials at Carbon. And so historically, I sort of divide the world of 3D printing into two major categories. One side, you have categories of printing that use thermoplastics and use heat to either fuse powder particles or extrude filaments in order to make an object. And so you have this whole area, and that would include your FDM type of printing, so your sort of MakerBot type of 3D printers, your SLS, so that's selective laser sintering, so this would be your powder-based systems like the HP machine or the more typical SLS machines. And then, so that's thermoplastics. And there, you have the advantages in that you're using known thermoplastics like nylon and ABS and PLA. And so they're materials that people are familiar with. But you also have resolution challenges there in that you're limited to, how thin of a bead you can extrude or how small of a powder particle you can make and how consistent that is. And so you can always, if you go to a 3D printing trade show, you can always pick up a part and immediately tell if it's made by FDM or by SLS. They just have a characteristic look. On the other side, you have 3D printing technologies that use liquid UV curable resins. And so this would be categories like there's ink jetting methods where like a polyjet, where I'm ink jetting a UV curable resin in a layer by layer format. Or you have your typical stereolithography categories where you might have a vat SLA where you have a large vat of UV curable material and you're sort of making this pattern with lasers. Or you have the, what are called DLP systems that make use of these digital optics. And so long story short, the UV curable side of the house of 3D printing can get you really great resolution that looks on par with injection molded parts. And that's because you get to use these advanced digital optics that have resolution, in the range of 25 to 75 microns, these little pixels of light that you can fine tune as you're doing your printing. But the problem is the materials that have been traditionally used in liquid UV curable printing, they all come from the coatings industry. And so there are mixtures of oligomers, acrylates and methacrylate oligomers and what are called reactive diluents, which are basically just monomer forms of acrylates and methacrylates. And so you blend all those together. And so you'll get a really nice looking part, but it's often very brittle compared to your typical thermoplastic materials. And that's because these are often very highly cross-linked UV curable networks, and the resulting properties can be quite brittle. And so we were looking at this problem in the early days of Carbon, and again, we had aspirations to go into production, so like midsoles and make consumer-facing parts. And so we decided to go a different direction and use what are called dual cure chemistries. And so we looked around, and if you're going to confine yourself to these UV curable chemistries, you really have a pretty limited scope of materials that you can work with. There's only so many things that you can put acrylate and methacrylate groups on, and you just have a limited range of chemistry that you can access, and therefore a limited range of properties that you can access. And so we were looking around, and started to think about, you have a lot of thermally curable chemistries. So, a 2-part epoxy adhesive that you might buy at the hardware store, or a 2-part silicone sealant that you also might buy. These are all chemistries that have a part A and a part B, and they can react. And polyurethanes can also fit into that framework, where you have a part A, a reactive part A, and a reactive part B. And there's a much larger, versatility of functionalities and properties that you can access with the thermally curable materials. And so we started to explore ways of combining UV curable chemistry with thermally curable chemistry. And so we would have these resins, again, that are dual cure. So basically, we take reactive chemistries like a polyurethane, a 2-part polyurethane, and then we add, and it takes some skill to kind of shuffle around the formulation components, but our formulations will have a part A and a part B, and we have the UV network mixed in, and we have the reactive thermally curable component as the part B. And so we kind of have these in cartridges, again, like you see at a hardware store, and they go through what's called a static mixer, which basically just folds the 2 parts together as it dispenses. And so you get really nice mixing, actually. So we mix all of this together as it goes into the printer. So then I start my printing process, and I'm projecting UV light in various patterns on a layer by layer basis and building this part. And then, so while I'm doing that, I'm activating my UV curable chemistry that I have in there. So I'm forming this initial network that's defining the shape of my part. And in the process of doing that, I'm actually entrapping the thermally curable chemistry in that initial network. And so I have the part in what's called a green state. So it's done printing. It looks like the part that I printed, but I'm not done yet. And so then I will clean the residual resin off. We have a variety of ways to do that. And then I take the part and I put it in the oven. When I do that, now I actually begin to cross-link and activate that secondary thermal network that, again, is entrapped in that initial UV network. And I get what is known in polymer science as an interpenetrating polymer network. And so now I have, and when I'm finished baking, now I have basically 2 sets of different chemistries that are in my part. And so this is really cool. So this is a technology that's been used in coatings before, but never really applied in the world of 3D printing. And so when we started to look at this, again, we had eyes towards the running shoe market, actually, because it was sort of recognized as this big opportunity in 3D printing, that if you could figure out how to make really great materials that met the requirements for running sneakers, but also could fit in a manufacturing workflow and print fast enough, which is another important innovation that we did on the hardware side. You can print these materials fast enough that to be relevant from a production standpoint. Then you could start to get into kind of mass production of 3D printing parts, which is what we wanted to do. And so looking at this problem, we started to look in at, well, hey, if we want to make polyurethanes. We know polyurethanes work as a class of materials in this application. Let's just figure out a different way to make the actual polyurethane chains rather than trying to make some other material that comes close but doesn't quite, meet the bar. And so that opened up this whole world of polyurethane elastomers, again, because now we have access to the thermally curable components, and I can put those in as precursors in my liquid resin. And during that thermal bake, I can actually chain extend to really high molecular weight polyurethane. And so that's how our process works. And so, yeah, we had to look at polyurethane in a new way and kind of disassemble the polymer and figure out how to reassemble it only using 3D printing. And this allowed us to get into, a lot of properties depend on a critical molecular weight in the application. It allowed us to get to those high molecular weights that achieve the durability, the UV stability, the hydrolytic stability, and all the other parameters that go into solving for a running shoe application.
That was like so much, but that was so cool as well. No, I loved it. I just wanted to ask Dave, do you remember from our ceramics class how we were talking about like green state and then like how you have to like refine it? It's just really cool to see kind of like the polymers and the ceramics principles kind of now like intermingling. I've never really seen that before, but the concepts are cool. You mentioned the critical molecular weight. I'd like to dive into that a little bit. Can you elaborate on why exactly it's important for like the end use application, kind of adding that context to that critical molecular weight?
So there's a concept called the critical entanglement molecular weight, where above a certain molecular weight, your chains are long enough to entangle. And there's a really famous plot that it's basically, I don't know, there's probably a dozen or so properties that fit into this. If you have property X on the y-axis and molecular weight on the x-axis, you have this initial rapid rise, and then it comes sort of a plateauing. And where that curve plateaus is your critical entanglement molecular weight. And so why that's important is for things like fatigue. If you kind of zoom in and on the cartoon version of this, as you're routinely flexing these materials, if you have those entanglements, it adds a toughness and durability to the polymer chains. If you don't, then you start to degrade them and put a lot of forces on them, and they eventually start to break, and then your structure will break down. And so this sort of getting to that critical molecular weight threshold is key. Other properties that have this, impact strength is a big one. Tear strength, I believe, is related. And so there's a whole lot of really important, polymeric properties that we care about and that end consumers care about as well. You don't want the lining of your football helmet to fall apart after one game. You want to keep that going for a few years. Same with your running shoes; they have to hold up for a period of time. So, and actually our partners will put these materials and components through, a lot of durability testing. And that's critically important for validating the material. So, but it all comes down to the molecular weight.
Yeah, I agree with Puneet. That's fascinating. I did have a few questions. So when we think about, you explained there's like your normal 3D printing with you melt filament, et cetera, or SLS.
Yeah.
Those seem to be more limited by what filaments can be put in due to the processing conditions. Could you elaborate more on how your new novel technique allows you, like, it sounds like 5 times or like magnitudes of order greater like variability in your final product?
Yeah, so I mean, there's pros and cons there. I mean, on the pros for the thermoplastics is a lot of times you're having conversations with a potential customer or user, and they have maybe been using glass-filled nylon in an automotive component for a really long time, and all their parts are validated to the properties of glass-filled nylon. And we might have, say, a dual cure epoxy-based resin that has a lot of similar properties to that material, but might fall short on a few things. And, it's just fundamentally a different type of chemistry. And so you're often having to go through this validation testing and have these conversations of, okay, well, what properties are most important to you? And okay, well, here's our material that has those properties, and let's validate them. So there's a conversation that needs to happen to kind of pull people away who maybe, well, I've always used nylon, like, why can't I just keep using that? And so the material has to fit into our framework of, it has to be within a certain viscosity range, for example, in our printer. It has to, cure fast enough so that we can hit relevant print speeds. It has to have a high enough green strength so that it holds together and we can have high accuracy parts during printing. So it's a complicated equation, but what you have working for you is now I have the whole landscape of UV curable chemistry and a whole landscape of thermally curable chemistry that my team can now access. And they, a lot of what we do is just mapping out formulation space, and we have a lot of software and statistical analysis tools that we can use to do that. But you just have a lot of choices, and you have a lot of options, and you can go in and finely tune the materials for a specific application. So sort of pros and cons. So, but we are creating a lot of new materials that haven't existed before, certainly not in the space of additive manufacturing. And so it makes it exciting to have those conversations, because you can sort of, hey, look, I have the impact strength, I have the right modulus, I have the right tear strength for all these properties. Let's go and try and validate it in your application.
From the application standpoint, I'm just curious, at what point did you realize, or like, did you develop the technology with those applications in mind, like the Adidas midsoles and the Rolland's baseball glove? Like, how early on in the process was that like part of the vision?
It's a really great question. It's actually something we talk about all the time. The initial elastomers for the Adidas application were definitely designed specifically for that application. And so this required working really, really closely with the Adidas team and with their validation test and going through lots and lots of iterations. And we found that process to be really valuable. And you have this idea in product development of of adjacencies. And so if you can solve for a particularly hard application, it's likely that your material will work in other applications as well. And we saw this play out where we solved for running shoes, and then Specialized comes along and they want to make bike saddles. And so, well, hey, they use polyurethane foam currently. Let's try our polyurethane lattice. And it happens to have very similar properties there. You have other adjacencies. If you solve for automotive is a big one. If you can solve for interior automotive, there's a lot of adjacent applications that will work for that. And so in the early days of the company, actually, we took a more generalized approach where we had a sort of a blank whiteboard of materials and, okay, what do we want to make? And okay, well, let's make an elastomer, and then let's make a rigid and tough material. And then let's make a material that has high temperature and a good balance of other properties. And so we started to just populate this formulation space with properties, combinations of properties that we thought customers would find interesting and useful. And then we started to shift towards, as we started to go to more and more production applications. It is a much different problem to make a generic elastomer that someone can just use for prototyping or functional prototyping versus something that's very tailored specific for an application. And so now we've started to move to this model where we're engaging with customers really early on in the process and starting to do this sort of that same type of validation and reformulation type of work, so that we know when we launch a product that we have validated applications for it, but we also expect that it's useful for things way outside of those applications as well. And so our philosophy on that has shifted over time. And I think if you want to be serious about production in 3D printing, you have to do that. If you're just trying to make a prototyping tool, it's actually less important. Then you might just, okay, here's an elastomer, here's a different elastomer with this durometer, or here's a different rigid material that has slightly different properties. But if you want to go into production, it's very key. And if you look at, the website for a company, like Sabic that makes nylon, you'll see they have hundreds of different grades of, very, very small iterations on nylon. And that's all because someone came in with an application and said, well, I needed to do this, and say, okay, well, let's tweak it a little bit. And so, we expect at some point to have a variety of materials at that level where no matter what a customer wants to do, that there's a material that meets their application.
That's super fascinating. I kind of anticipated that it would be like applications driven like early on, but it's cool that there was also like applications that kind of derive from that, or like your materials could fit other applications just because there was that need in this space. But now I wanted to kind of talk about a recent carbon development, which is a plastic material that is completely flame retardant. And so that is fascinating because usually like plastics are kind of thought to like melt or degrade at high temperatures. So what kind of possibilities does that open up, this flame retardant material that wasn't previously possible in this space or within carbon?
Yeah, no, it's a great question. So just to clarify what that phrase flame retardant means. So there's different levels of that, and the highest of that being a level called the V0. And so the way they run these tests are, it's kind of what you'd expect. You have a test bar, and then you apply a blowtorch to it for a period of time, and then you pull that blowtorch away, and you look at how long it takes for that flame to go out. And so a V0 rated material will almost immediately extinguish as soon as you remove that flame. And that's what our new epoxy 86FR product does. And so this is useful in terms, if you think about, if you had a short in your servers, you have these electrical enclosures that are typically made of flame retardant materials that can sort of contain that fire. So it's not like, it's wrong to picture something like steel that is just like impervious to fire. So the material is degrading, but it's not igniting. And when that source of flame removes, it completely self-extinguishes. And so this is a category of material that we worked on for 3 years, actually. And it was really challenging because I always draw the analogy to a lot of what my team does is sort of like solving a Rubik's Cube. So each face of the Rubik's Cube is sort of one property. that you're trying to solve for. And it's typically easy to kind of solve one or two, and then the rest are all messed up. And so you're often having to go through these, formulation mapping exercises and working through the algorithm to solve for the entire picture. And so in this case, we were trying to solve for, we wanted a V0 rating for flame resistance, but we also wanted something that was functionally tough, that met the other requirements. So we had a material that's also a dual cure epoxy called EPX82, which has been a really great workhorse material for us. And we started to think about ways we could tweak the material, that material, to make it flame resistant. And so with some monomer changes and a lot of formulation work, we were able to find that balance of V0 rating with functional toughness, meaning it has decent impact strength, it has great thermal stability, so it has a TG above 120 C, but it also has a high modulus and just good workable properties. So for, when you picture things like electrical connectors or electrical enclosures, those can't be super brittle, just because they're FR rated. And so that's sort of how we arrived on that. But yeah, it's a really unique material in its class, because there are other FR materials within 3D printing, but they tend to not have the toughness that we're able to achieve with the 86 FR product.
So when we talk about applications being driven, and you've been working on it for so long, I guess, why would a polymer that's flame retardant be useful in industry, or what would the applications be other than a server? Is that really like the driving, or are there other applications we could apply it to?
So, you think about a lot of medical equipment or hospital equipment. If you have some of that catches fire, that can be a really big problem. So that's important there. There's aspects of the transportation industry generally, whether it's automotive or trains or aerospace, where VR materials or FR materials are really important. And so those are sort of the main areas, where industrial applications, automotive, aerospace, transportation, those types of things.
And so now that you walked us through like that development cycle, you've talked a lot before about, or the Rubik's Cube analogy is that you have to tune your polymers. And so for polyurethane especially, there's different products because its building blocks can be interchangeable. Carbon takes us one step forward, and you mentioned this, but it designs lattices to enable more tunability of the pure polyurethane products. Could you give us an example and maybe walk us through how that iteration works on top of what you already do is just changing the polyurethane itself?
Yeah, great question. So, a great example that I like to point to is if you take a standard bike saddle, they usually have a cover on it, and you take that cover apart, you'll see that there's actually maybe 3 or 4 different types of foam that are in that saddle, and it's often cut and taped together so that you have regions of differing stiffnesses. So, under the sit bones, you might want, more support than in the middle of the saddle, for example. And that speaks to something. That means the only way you can change the properties of a polyurethane foam are by changing the chemistry of the polyurethane foam. So you have to make a different foam if you want to make it softer or stiffer. If you look at our saddle that we make with Specialized or Cell Royale or other companies, with the exact same material, we can have a wide variety of different durometers, essentially functional durometers within the seat. So you can have very stiff regions where the lattice is very dense, and you can have very soft regions where the lattice is less dense. And that matters a lot in terms of comfort and in terms of the transition from one zone to another. You can very nicely tune that with lattices. So we have an amazing computational geometry team here at Carbon. We actually just recently launched our first standalone software product. It's called Design Engine. And so using that product, and you actually standalone, what I mean by that is you don't have to have a Carbon printer to use this software. You can just download it and start playing with it. So from there, you can input a solid part in the form of a CAD model, and you can input the types of mechanical properties, the compression profile that you might want from a lattice. And it will go through this computational algorithm and generate a lattice for you that meets those requirements, and which is really, really cool. And so what's fun about that is that, it's probably one of my favorite things about Carbon is you have software engineers and hardware engineers and material scientists all working side by side and kind of often looking at the same problem and coming up with very, very different approaches to solving that problem. And so when you can combine those types of fields, a lot of magic happens. And so, we often look to, solve lots of different types of problems using software, whether that's mechanical compression response using lattice generation, or even changing the way a material prints. You can change the properties of the end material by adjusting the software algorithm in the printer. And so there's a lot of close collaboration between my team and the software team and other teams at Carbon to make all that work. But yeah, that's really one of the key, powerful aspects of lattices is the tunability. And so this design engine product will generate your lattice, and then you can also adjust the transitions between those different areas, and you can have different densities of lattices, different types of lattices in different parts of the same overall same object.
And so you say that you work with software and hardware engineers. And one thing that's really interesting is this algorithm sounds fantastic, but whenever you build an algorithm, you have to validate it. And I think that would fall on you specifically. So as a science or a leader in general, what is your philosophy on validating like new technology such as this in the most efficient way possible?
Yeah, that's also a really, really great question. We run into this a lot because when you go into production, you're right, our customers who are manufacturing these products, they will validate a material, they will validate a geometry, and they'll validate a workflow. And any deviations from that means it has to be revalidated. And that becomes especially problematic in the medical space where you would have, the FDA approves a device. They don't approve materials, they approve devices. And so if you change aspects of your material or geometry, depending on the degree of change, you may have to revalidate. So the way we do this is we have the ability to selectively lock. We basically call them lock builds. And so our customers will go through, various design. They go through a lot of prototyping and functional prototyping and validation. It's actually one of the powerful aspects of 3D printing is that you can screen, 100 different designs in a matter of weeks. Whereas if you're trying to do that by any other method, you're having to either cut tooling for each of those designs or do subtractive manufacturing to change your designs. And additive allows you to do that very, very fast. And so you can do that very, very fast and arrive on your optimized geometry, and then you lock it. And then you can lock your workflow, but we can also lock the printer algorithm for that particular build so that even as our software continues to upgrade, that particular build will not, and it will print the same way that it always has been. So again, it's very helpful to have a flexible software approach. So one of the decisions we made early on in the company was to have the printers network connected, meaning that they can receive over-the-air software updates. And we will ship these periodically, every 4 to 8 weeks. And, just like your phone updates or cars are updating now, our printer updates and gets better and better over time. But this did create that same problem you're pointing to as a customer going, wait a minute, I'm in production with this build, you have to let me keep my properties the same. And so we have solutions for that as well.
So what is your vision then? Because David and I have heard in several previous episodes, just the potential of like computational material science, machine learning, and AI in this space. What is your vision? Because this design engine product seems really fascinating, really cool. What does that look like? How is that going to be developed 5 years down the line? And just what can that evolve into?
Yeah, I think one of the big visionary things that is necessary is to make more and more students and young professionals aware of these tools, because mechanical engineers will tell you that they're taught all of the rules of injection molding in school. And so when they go to design a part, when they get a job at a company and they're asked to design a part, they do so thinking from those design constraints. And so there's a lot of education and awareness that we need to generate that, hey, additive has reached the next level and it can now create very high performance parts. And you haven't thought about the rules for lattice design, but here's all the great things that lattices can do. They can make lighter weight parts. They can make parts that manage heat management much better than a foam, and they can make parts that do energy attenuation in very different ways from foams and other aspects. So there's a huge educational point of this, but yeah, it's super fun to start to think about merging of this sort of design flexibility in geometry with design flexibility in materials, and so my team uses, sort of these formulation statistical mapping programs to be able to map out the space. And from, running 20 different formulations, you can map out a very large property space. And I've often talked about, it'd be really interesting to merge those two things where for a given, performance or property input, you output a combination of geometry and material. And so I think that's one of the places where this is all headed. But it really does allow you just such a versatility in terms of your design.
Okay, cool. So now kind of the main focus, I guess, of the episode, or the thing I was looking forward to the most is the sustainability side that comes with 3D printing, just because we've heard that there's just there can be lots of waste generated from these processes,
Sure.
like excess resin, chemical cleaning agents, etc. But Carbon is implementing sustainable methods to kind of tackle these challenges. So can you just discuss that in more detail? What is Carbon doing to make 3D printing more sustainable?
Yeah, absolutely. So this has been a big push of ours for several years now. So the types of things that Carbon specifically is focused on, the first is the exact problem that you mentioned, that 3D printing in particular, in that liquid resin side of 3D printing, does generate a lot of waste and can be very messy. And so this is something that we looked at, again, with your first application can help you solve a lot of problems. And so as we had eyes towards, okay, we have printers, we have materials that meet the requirements for running sneakers. Now we need to think about factory workflow and how are we going, what do these processes look like? You very often find that if your sustainability needs and objectives are aligned with your economic needs, then things can go very quickly. And so we had both a sustainability problem in the form of what are we going to do with this resin waste, and cleaning with solvent, kind of sucks, and it generates a lot of hazardous waste, and nobody really likes doing it. How can we solve that? And on top of that, it's expensive to dispose of hazardous waste. It's certainly expensive to waste resin that has gone through your whole supply chain. And so our mechanical engineering team started to think about different ways to clean parts. And one of the things they came up with was this spin cleaning technology. And so we have these spinners that hold 3 of our large build platforms. And so you can imagine, the printer, the platform goes in, your parts come out and they're dripping with resin. You take that platform and you put it in the spinner, and then you do the same with 2 others. And then you close the lid and you turn it on, and this thing starts to spin very quickly. I think it goes up to about 600 RPM. And that action by centrifugal force, you're driving all of that excess resin to the walls of the spinner. So it's sort of this cylindrical shaped device. You put your platform in, and then you start spinning. So all of the excess resin gets flown off to the edges of this. And then it's designed so that we can collect all that and then, fill up a container with all that excess resin. And then that just goes right back into the printer. And so the parts that come out are very, very clean. And they have this very thin film, about 50 microns or so of a residual resin that's still on the part. But the cool thing is you can account for that thin layer of resin in your design. And so you can account for that. And so then again, and also because we're using dual cure technology, I take that part, put it in the oven, and that thermal chemistry activates. And out of it, I get a perfectly usable part without ever using any kind of solvent to clean. And so this solved a major problem for us, both on the sustainability aspect, but also on our economics of production, that get much, much better when you start to factor in resin recovery and elimination of solvent cleaning. So this is one big area. We use this type of cleaning in all of our high volume applications, which would include the midsole applications. It includes our helmet padding applications, the bike saddles. And we even use it in our thermoforming business. So going to a completely different industry for dental models, same workflow. So we can print dental models, they're dripping with resin, you put them in the spinners, collect it. And again, that's an industry where, every penny that you could, that goes into manufacturing that part matters. So this spin cleaning technology has been really successful for us. And we actually run the numbers on how much waste we would have created in these types of applications. And we're up to, I think, several thousand metric tons of hazardous waste that just never existed because we do this by the spin cleaning approach. And for frame of reference, an Olympic-sized swimming pool is 2,500 metric tons. And so we're well past an Olympic-sized swimming pool of hazardous waste that has just never been created. So that feels really good. And, again, has also helped us drive a lot of things to production. So that's sort of the first thing we're doing on related to cleaning. A second major focus for us is in the area of bio-based materials. You often hear these referred to as bioplastics or things like that. This is a really hot topic in polymer science right now. It's a really hot topic in industry where, there's basically two sources of nearly all the chemicals that you think of, certainly all the organic chemicals that you think of. One is petroleum. And many of the common plastics that we use every day, polyethylene, polypropylene, those monomers are byproducts of the oil refining process. And so there's something like all of the plastic annually made in the world is like 5 to 10% of the oil that is refined in the world. So this gives you a sense for the numbers of the amount of oil that's used. But that's a limited resource. And we all know the problems with the carbon footprint and just the issues with oil in general. Bioderived sources are a second major source. And so here you can use plants or microbes and fermentation to create building blocks for polymeric materials. And so one of the products that we have just recently announced is an elastomer called EPU44. And this is our Gen 2 elastomer material for the Adidas running sneakers. It has a lot of performance advantages. It's a stiffer material, so it allows us to make lighter midsoles. It has very nice energy return. It has all the durability aspects that we talked about. But it also has a much higher green strength than our Gen 1 material. And that allows us to make different types of lattice structures that otherwise wouldn't be printable. And so this has been really cool. So, but one of the other things that we did with EPU44 is we started to look at, remember we talked about the soft segment components of polyurethanes? So there's a company that makes a product called Sustera. So the company's DuPont, Tate and Lyle, and they have a monomer called Sustera, which is basically just a 1,3-propane diol monomer. And that monomer is derived from corn. And so they can take corn, isolate the sugars, and then refine the sugars to get to that 1,3-propane diol product. And you can then polymerize that to make an oligomer of a polymer chain for your soft segment polyurethane. And that product's called PO3G. And there's a number of manufacturers that make that. And so we started to look at this product. Initially, we were trying to solve a viscosity problem, and the PO3G oligomer happens to have a much lower viscosity than the typical PTMO materials that are used in polyurethanes. But it also had this really exciting bioderived aspect to it. And so you can imagine you can make your products from petroleum, or you can basically make them from CO2 and sunshine in the form of a plant, and then have the plant, the machinery of the plant, make your building blocks of your polymer for you. And that's a much more sustainable process. It's a much lower carbon footprint on the overall material development. And so there's numbers from DuPont, Tate and Lyle that it uses 56% lower greenhouse gas emissions in the production of that material versus the standard, petroleum route. And so we saw this as a really exciting opportunity. And our partners at Adidas, they're incredibly focused on sustainability, and it's a major aspect of their business. So it was sort of a win-win for everybody. And so we incorporated this material where EPU44 is 40% by weight derived from this plant-based raw material. We also have a rigid polyurethane material called RPU130 that has about 25% by weight of this plant-based soft segment. And that's a very high temperature, high impact strength material. So one of the things I like to point to is you don't have to compromise your performance in order to go with the more sustainable approaches. So the plant-based raw materials are a really exciting focus for us, and we're looking to do more in that area. Just want to make sure we're not running out of time. We look at, latticing itself, and part lightweighting has a lot of great aspects to it from a sustainability perspective, where, again, this reduction, just the simple reduction of the amount of material that it takes to make a part, that's a benefit in and of itself, because you've pulled out a bunch of material from the part. But also in industries like, electric vehicles or vehicles in general, they look at every ounce of weight that goes into that car or airplane or whatever it is. And the more that you can pull material out of that and lightweight those parts, the more fuel efficiency you get out of that part. So latticing in general has this big opportunity in terms of fuel efficiency and these types of approaches. There's other areas that it's sort of common to really all additive manufacturing, and this idea of localized production. And so basically, manufacturing the parts that you need, where you need them, when you need them, can help reduce a lot of this transportation costs of, making resin in one country, shipping it over, injection molding parts in another country that are then packed up and then, put on boats or planes and moved somewhere else. The supply chain, as we've learned, is incredibly fragile over the past couple of years. We've seen this, and additive manufacturing can play a major role in solving those problems, but also in a more sustainable approach. Finally, we have a couple of projects that we're working on in terms of recycling. Recycling, we could probably do another few hours on, but recycling is another very hot topic, both in academia and in industry, where people are realizing that the current way we go about this is pretty broken. And there's some really different aspects. There's a really exciting area called chemical recycling, where instead of just melt processing a part, you actually break it back down to the original monomers and then purify those, and then remake your polymer. And so you can, get to these closed loop type of systems. And so we have efforts in both mechanical recycling as well as chemical recycling for within the space of 3D printing. So that's just a very quick overview of some of our efforts in sustainability.
That's awesome. That's awesome. So it's very evident that there's a lot of measures that Carbon is taking to just make the 3D printing industry more sustainable. And it's cool to see your partners are really on board with that too, especially Adidas. And so I guess we can kind of just like wrap up this episode, and we'd love to hear your thoughts on why our MSE audience, our listeners, should consider working for Carbon if they're interested in 3D printing.
Yeah, well, I'm biased, but I think it's one of the most exciting companies out there in the material science space. And I guess one aspect I mentioned is this: it's a very, very collaborative company, and we have to be collaborative, because at the end of the day, all that matters is the part coming out of the printer. Nobody cares how clever the chemistry is or how amazing the code is or all the hard work that went into the machines. They care about the quality of the parts coming out of the printer. And in order for that to happen and to hit the right standards, we all have to collaborate together. So, you have the opportunity to learn about, very different fields in computer science and mechanical engineering. And, we have a whole team just dedicated to the physics of the printing process and understanding that at a really deep level. So that's one aspect, is that the collaborative nature. From a material science standpoint, my team gets exposed to so many different types of materials and chemistries. It's sort of, you open up the polymer textbook and, we're doing something, whether it's elastomers or medical grade materials, or we have projects in bioabsorbable materials. It just kind of covers the whole spectrum, and it's never boring. There's always a really interesting project or problem to go work on. And I think many of us got into material science because of the number of industries that you can impact with this sort of base level understanding of how to make materials and how materials work. And I think of Carbon as sort of the ultimate embodiment of that, where it's a magic box that will print whatever you ask it to, and that's pretty exciting. And the range of industries that we get coming through the door is fascinating to me. So whether it's a consumer products company making running shoes like Adidas, or automotive components or medical devices, or we've had people come in from tractor companies, and almost any industry you can imagine, there's applications and problems that additive manufacturing can help solve.
That's awesome. Yeah, if we had another hour, I'd love to ask you more about like the medical grade stuff. I'm in that industry, or like the Rawlings baseball glove, but maybe we'll do a part 2 sometime. But it
Yeah,
was a
that'd be
pleasure
fun.
having you, Jason. We really enjoyed learning about carbon and all of the potential applications of polyurethane, and yeah, just your technology as a whole.
Awesome. Well, thanks a lot, guys. This was super fun.
Yeah.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.